All right. We're here in the Levin Center for IHMC Research in Pensacola, Florida, to give an update on the progress on our Fast Runner project since we went on Discovery Channel with the elliptical runner. I'm Johnny Godowski with the Fast Runner project, and here is Dr. Chris Smith-Wedicombe, our chief designer and simulator, and we're here to talk about all the exciting factors that make fast running as simple as a wind-up toy, only dynamic and reactive and self-stabilizing and resilient and all that. Chris, say hello.
Hello.
What have we got here? Show us what we're looking at.
Oh gosh. Oh, we've got.
We've got this awesome machine here in the simulation, and here it is running really, really fast. Come on, zoom in. Show that, right? And it's going really, really fast, over 10 miles an hour. Look at that, look at that. That's real time now. Really, really fast. Amazing. I think we're the fastest running biped, at least built this way with segmented legs. And this simulation is the most advanced on the planet, with the ground reaction forces converging, emulating things in nature. Here we are stepping high. We'll show, as we go through with Chris, what all these arrows mean and why it's important, why this drive is important here. We'll show you on the machine all of that, including what's going on in here and what we're looking forward to and about to do. So, Chris, go ahead, step on frame and start showing us these features and why they're interesting and why they matter and what's exciting about it.
Okay, well, see, we've got a new prototype here. We've made some significant design changes since our planar robot ran on the treadmill. And it's based on a progression of insights that we've come across in simulation. Let's see, I guess there will be probably 2 or 3 major innovations.
Well, sure. Tell us about this drive. It's more compact than the elliptical. Using an elliptical drive, maybe show us that in simulation and show us what these parts are, why the rubber bands are important, and what we're seeing in the simulations.
Okay, well. So we have
if he shows you something, zoom in on the camera so the camera can see.
The elliptical drive mechanism here is a more compact version of the similar elliptical.
Can we get it moving slowly so he can zoom in and show everybody?
Mechanism that we had on the planar prototype.
So this drive with these cranks and belts are making this point on the leg go through an ellipse. And because it's a zigzag pantograph, the feet go through a similar ellipse. Now when things get dynamic, those are taken into account and you can see the foot traces on the simulation behind you. So here we are going really fast. And that's kind of slow. In a moment we're going to go real time. And when we go that fast, flexibility in the structure causes oscillations that can get out of hand. And we'll show you that too. Here's our simulation with the machine as it is, working as intended. And
I'll fix it.
We want okay.
Yeah.
Okay. Okay. Well, there it is. And we could get that one playing too, right?
Yeah.
So in the middle, you see it running around a curve. Chris, what is this simple planar demonstration showing?
Yeah, this is just a very simple concept demonstration of using finite width.
Okay, let's get this one here and talk to this. Just click OK. So Chris, tell us what we're looking at.
Okay. So having instead of using point contacts for the ground, having a distributed toe segment allows us to achieve some sort of yaw roll coupling that is important for turning the robot when it needs to. So that as it leans side to side, it also turns appropriately. Yeah.
So we've got the hip here, the knee, the ankle, and right here, the ball of the foot and the big toe.
Yep.
And having that big toe move sideways a little bit helps stabilize it, right?
Yeah, so that's another. Oh, let me stop. But if you watch running birds in slow motion, you'll actually see that as they hit the ground, the foot actually rotates slightly. So
Yeah, show that motion, see? That little bit of compliance there seems to help in our simulations
yeah,
with lateral stability.
having lateral compliance in the right direction, well, about the correct axis, seems to reduce spikes in the ground reaction forces that will help us run stably without the polarizing.
Now, I will say, and Chris, I want your opinion on this. We've got some lateral compliance here. That's not what we see in the birds. Instead, the knee itself kind of twists and gives that lateral compliance.
Right.
Isn't that right?
Yep. So the X-ray motion capture shows that a lot of the steering that birds do is accomplished with long axis rotation of the tibia and tarsus. I'm sorry, femur and tibia.
So the knee moves a little bit sideways like that as it bends, and that gives us the same motion here that we've done with this joint since we had that built already. And the research just came out, so we're up with the very latest, and it's working.
Yeah, it's promising. Of course, it would be nice to be, have some degree of active steering control, so to speak, in this joint, but it's probably something for more advanced work type.
So when we see here the high speed, when the vibrations get out of hand, what happens? Oh, well, there we go.
Goes to the next one.
We can there we go. So that's the most advanced simulation of what we intend to do, and in simulation it works as intended. So this is very promising. And you want to hook up these rubber bands and actually run at high speed on the film for us?
Sure.
Can we do it? Explain why the rubber bands have to be hooked up for higher speed.
Well, yeah, so the way the rubber bands are connected here, they
Move
help.
in so we can see it.
As the leg extends, when it's forward, gravity is also trying to extend the leg even further, so having the rubber band helps counteract that force so that we get a smoother leg motion. So let's give it a run. Yeah, hold this guy down. Wait a minute. Oh, I think the vibration set off our little.
All right. Let's go.
Let's not kick the TV.
All right, I saw a part come off.
Yeah,
See that little thing?
Yeah.
So let's fix that while we're right on it.
This is all 3D printed plastic, so
There you go.
that's how it goes. All right, need to fix that.
At least
So-
we got a little bit.
The speed was 10 miles an hour. We've got a 10-mile-an-hour treadmill here. When Chris is satisfied that the structure is capable, we'll remove these glass walls and try our first trials on the 10-mile-an-hour treadmill right here in the lab, where we can use our high-speed cameras to diagnose anything that's wrong. We're very excited about getting something like this to work on the treadmill and on the open road, hopefully before dynamic walking in May.
You have any last words?
I think we're ready for the road. Let's go.